Okay, right. Assalamualaikum and good day, especially for my student from Group 2. Before I start, we start with the dua first. Bismillahirrahmanirrahim. Allahumma inni as'aluka ilman nafi'a wa rizqan thayyiban wa amalan mutaqabbala. Rabbi sadri yasir Rabbi sahli sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Birahmatika ya arhamar rahimin walhamdulillahi rabbil alamin. Okay, terlebih dahulu saya minta maaf lah sebab saya dah janji dengan student grup 2 ni saya nak buat kelas revision, tapi memandangkan baru-baru ni kan saya agak sibuk, dan saya pun dah cakap kan sebelum study week ni, seminggu sebelum study week saya dah mention pada student grup 2 yang saya ada saya ada kursus selama 2 hari, jadi saya tak sempat nak buat lah. Lagipun saya tak berkesempatan lah nak buat revision class face to face, jadi saya rasa better saya buat online lah rasa. Jadi tu lah terlebih dahulu saya minta maaf lah, saya dah ganggu kamu semua ni sebab saya punya style, saya tak suka kalau nak buat revision kelas ni waktu weekend, tapi itulah saya tak ada nak cari masa yang sesuai kan. Jadi memandangkan kamu semua exam nak dekat dah hari Selasa, jadi saya kena buat jugalah. Tapi itulah saya kena buat, mana kata saya dah ganggu lah. Saya rasa ni first time saya buat kelas weekend. Selalunya saya takkan buat kelas weekend. Kelas weekend ni bagi saya, kalau macam dulu saya just student part time degree ataupun student master, saya buat lah. Jadi kalau student degree ni memang kalau betul saya nak elakkan daripada nak buat kelas weekend. Tapi for the sake of revision, I think I have to conduct online revision class during weekend, especially on Saturday or Sunday lah. Tapi saya pilih Saturday lah. Okay, baik. Okay, overall, you need to remember one thing, that you already learned power system analysis topic. And then, okay, wait first. I record it first. And then, you need to understand the topic first. Actually, the fourth topic and the power system stability will cover in your final exam question. So there are 4 questions. 4 questions, 3 hours, 60% final exam. So there are 4 questions. Question 1 and question 2 basically on the fourth topic which covers fault calculation using Thevenin theorem. And then another question will be covered on unsymmetrical fault, which cover single line to ground fault, double line to ground fault, and line to line fault. And also you have to know the basic formula for all these 3 types of unsymmetrical fault. And then for question 3 and question 4, basically on the power system stability. So I hope that you already do your tutorial, especially your tutorial question. So for tonight, I would like to show to all of you the tutorial question that I already did past a few weeks ago. Okay, I will start with this one first. Tutorial 2, fault analysis. I think we already discussed on tutorial 2 fault analysis, but basically when we see this first question, this is actually for symmetrical fault. With symmetrical fault, by using the network reduction method, it means that you have to calculate the fault current using the Thevenin theorem, which means that before you need to calculate for the fault current using the Thevenin theorem, you must know the 5 basics of per unit system, which means that the 5 steps that you need to know. So basically from this question, we can see that given that this figure 1 here, we have 4 bus, and then we have 3 generators here, and then we have this respective zone, which is I divide into 3 zones. zone 1, zone 2, and zone 3. And then I have the rating, I have the nominal voltage, and I have the XO, which is the reactance O, for each component, for generator 1, generator 2, generator 3, transformer 1, transformer 2, transformer 3, and also I have also the reactance for each 500 kV line. So from the question given, question asks about, you need to determine the Thevenin's reactance in per unit at the fault, which means that you have to find the fault, okay, by using the Thevenin reactance. And then for the part B, you need to determine the subtraction fault current in per unit and in kiloampere, which is the actual value in root mean square. And the part C, you need to determine contribute to the fault from data 1 and from line 1 to 2. It means that from bus 1 to bus 2. So basically, I already discussed with my students, especially my group 2 students. So this is the solution that you need to do. The first thing you need to do is, you need to remember one thing that you already learned, especially when you learn with me last semester on power system engineering subject. You have to remember one thing. You have to remember the formula here. You have to remember the new X for generator 1 equal to XO generator 1 times the V base old divided by V base new square, and then times the S base new divided by S base old. Okay, this is what you are learning from me. But in terms of this solution, we can see that there is no V base old divided by the V base new, because in this solution that I already provided by the other lecturer, because he or she already know that V base old and divided by V base new is the same value. So this is the reason why in his or her solution, we can see that there is no V base old divided the V base new. He or she try to put just write S old per unit times the S base new divided by the S base old. But the main thing is I want you to follow my style. So my style is by using this standard formula here. I want you to maintain this one because I'm afraid that, let's say if the V base old and the V base new will have a different value. So how about different value? It means that the answer should be different from J0.4 per unit. But in terms of this generator 1 here, calculation, you can see, I know that some of you might confuse with this one. Oh, doctor, how come this solution here, we don't have the V base old divided by V base new? Because he or she, which means this lecturer that already did this solution, he or she already know the V base old divided V base new is actually the same value. So that's the reason why he or she didn't put in terms of in this solution here. So the basic thing that I want all my students to do is you need to write this way. Saya nak awak buat macam ni. I want you to write this way. This is the better solution in terms of writing formula. Okay, and then for the and then okay, xg1 equal to xgo, okay, xgo J0.2, and then this one S base new divided by S base O. Okay, one thing that you need to remember, because the S base O is actually from here, from this rating here, S base O 500 MVA. But for the S base new, which is starting from here, starting from generator, from zone 1, going to the zone 2 and going to the zone 3, which means that we have to use 1000 MVA. Okay, this is the basic that all of you should know because you already learned the power system engineering. So from here we can get the exact value for xg1, which means that xg new, which means when we calculate by using this standard formula here at the top here that I write, so we have J0.4 per unit. And then for the xg2 also we can see that the x old, okay, by referring to this value here, we can see that the reactor is J0.18 per unit. You just write this value, and then divide times 1000 divided by 750, which means that J 0.24 unit. Or, okay, one thing that you need to remember that I want also to all of you to write V base O divide the V base new, right? So from here, we can see that the generator here, which is at zone 1 here, zone 1 here means that this is the value for the V base O, which means that 13.8 kV. If you remember one thing, that you need to calculate the V base new, right? V base new, which means that at the zone 1. So by using the standard formula, which means that you use the voltage ratio. If you can remember, my second step, if you need to calculate for the V base, hopefully you can remember. The V base 2. V base 2 means that the V base at zone 2 and then the V base at zone 1, which means that equal to the V base 2 is actually the secondary side of transformer 1, which means that the V secondary transformer 1 divided by V primary transformer 1. But the main thing that you need to know, because in the given question, this one is actually the V base, right? This one, the V base 1, which means that 20 kV. In order to find for the V base 2, which means you have to calculate V base 2 is equal to V secondary of transformer 1, which is 13.8 kV. And then you divide with V primary transformer 1, which is, oh, sorry, but this one my mistake. V secondary transformer 1, which means 500 kV. And then divide by V primary. V primary is 13.8 kV. And then you have to multiply with the V base 1. That's why you need to multiply with the V base 1. The V base 1 is actually equal to 20 kV. So from here, you can get the answer for the V base at zone 2. And then also you have to determine for the V base at zone 3 and so on. So you have to do the calculation for each respective zone. And after you find the value for the V base 2 and the V base 3, and after that you can do this one. Okay, this one, you should have the V base old value here, and then the V base new, so that you can cancel out the V base old divide base new, because it's actually the same value, and then equal to 1 square equal to 1, and then you times with the 1000 MVA divided by 500 MVA, so then you have the answer is J 0.4 unit. And also you can apply the concept here, the formula here for XG2 and also for XG3, the reactance of generator 2 and generator 3. Then you have the answer as in this solution here. And after that, you have to find what? You have to find transformer 1, right? The XT1. XT1 equal to XT old, which means that the XT old is actually J 0.12 here. J 0.12 per unit. And then you have to times the V base old divided by V base new. You can do it by yourself, and then you have also the same value, which is equal to 1 square equal to 1, and times the S base new 1000 MVA divided by 500 MVA. Then we have this answer here, J 0.24 unit. And also you can apply back this formula here for transformer, and then you have the answer here, J 0.133 per unit, and also for XT3, J 0.1 per unit. Okay, this is basically when you need to calculate the new reactance for each component in power system for generator and for the transformer. So basically we have already discussed, especially from one student from Grade 2, we have already discussed this one. Step number 1, what is it? We have to identify the S base and the V base given in the question. And then for step 2, you have to calculate the V base for each zone. And then after you find that one, you have to calculate the Z base. Okay, this one actually the Z base here. This one, Z base here. You have to calculate the Z base, which means that the Z base as the transmission line, which is actually at transmission line here, which is at zone 2 here. So from here, we can get Z base equal to V base square divided by S base. V base we don't already know because for the V base at zone 2 is actually 500 kV. So 500 kV square divided by 1000 MVA, which is the S base that we use from step number 1 here, S base 1000 MVA, which is given in question. And then we have the answer is 250 ohm. And of course, you have to identify the value in per unit because this was base, right? If you remember one thing, that per unit is equal to actual divided by base. Actual actually given in the question. You can see that in this question, we can see the value here, the actual value here, J50 ohm, J50 ohm, and also we have here is J50 ohm. So from here, we can see that we already know J50 ohm. And then from here, J50 ohm divided by 250, which is the base value here. But remember one thing, when I did taught all of you last semester, you need to memorize the formula. Z base equal to V base square divided by S base, which means that the V base equal to 500 kV square divided by 1000 MVA equal to 250 ohm. This formula, I hope that all my students can remember. This is very, very important because in order to find the per unit value, you need to know the base. You need to know the base formula. Okay, then from here, the actual here, this is the actual, this one is base. So we have the value in per unit value. Okay, this is the basic concept in per unit. I hope that all my students can remember. I mean that if you not remember, you can find my previous lecture note, especially in power system engineering subject. Okay, from here, after you finish step number 4, you have to calculate the reactance of each component in the power system in the power system network in per unit. After you finish that one, you need to go to step number 5. Step number 5, you have to draw. You have to draw the reactance diagram, which means that you have to draw the per unit equivalent circuit according to the singular diagram. So singular diagram here, you need to convert it into the per unit. So this is how you solve. This is how you solve how to draw, how to sketch the singular diagram in per unit. So basically, this in blue color here, we can see that this is generator 1 here. In generator 1, we have the voltage source, which means that in series with the reactance of generator. Okay, this is when we try to sketch or we try to draw the generator 1 model. So you need to have voltage source and also the reactance. Okay, this is the basic that you need to know. And then from transformer, we have to draw the reactance here, the reactance of transformer. We label it as XT1. And then going to here, we can see that this is X line 1, J0.2 per unit in green color here, in green color. And then we have this one, X line 3, J0.2 per unit, which is the line that connected from bus 2 to bus 3. And also we have the X line 2 here, X line 2, which means that the line, the transmission line or the cable that connected from bus 2 to the bus 4. And also we have here XT2 here, which means the reactance of transformer 2. And then we have another one, another generator, which means that generator 2 here. And of course, if you want to draw generator, it means that you must have the voltage source in series with the reactance of generator 2. So then another one, we have a transformer tree here, okay, that connected from bus tree here and then going to the ground here. So bus tree here, which means the transformer tree here, we have the reactors here, the reactant value, and then we also have the generator tree here, which means that voltage source in series with the reactance of generator tree. So this is how we draw the per unit equivalent circuit or the reactance diagram. Okay, after you finish from step 1, step 2, step 3, step 4, and step number 5, which is this one, the last one, and then you should go to step number 6. Step number 6, you have to determine the Z Thevenin or Thevenin equivalent reactance. Okay, how to determine this one, equivalent reactance? You need to take a look back at the step number 5 here, because here we can see that this is the fault here. The fault occurs at bus number 1 here. When the fault occurs at bus number 1, which means that this should be in parallel. It cannot be in series, which means that there is an obstacle here between generator going to the bus number 2, which means that the fault occurs here. You need to put it in terms of the parallel network. So from here, we can see that this one, J0.4, the XG1, which is in series with the XT1 here. So this one you should plus, you should add it together. So we have J0.64 per unit. So that's the reason why here, okay, like this one here, I already write like this one, J0.4 plus J0.24 parallel with this one. Okay, this one, you take a look here, you can see that this is actually J0.2, right? Okay, this one is parallel, right? Parallel with this one. So you have here, this one, J0.2 plus J0.133 here for the XT2 plus J0.24. And then you need to parallel with this one, J0.2 plus J0.1 plus J0.17. Because this one is in series, right? So you have to add it together. The same also goes from here. We have to add together. But remember one thing, this is actually in parallel, right? So this is why when I write this one should be in parallel. Parallel with this one is add together, parallel with this one, and then plus with this one, which is J0.2. J0.2 is coming from here. This one, the X line one here. So this one you add together. So then you solve this one, you simplify this one. So you have the answers like this. Okay, in per unit. Okay, this when you obtain this kind of answer for Thevenin equivalent reactance, then the main thing you need to check back at the given question. This one. After you solve part A here, you have to determine the sub-transient fault current, right? Which means that you need to know one thing is you have to find this one first, the pre-fault voltage. Okay, the pre-fault voltage. So the pre-fault voltage from the given question, this one, which one? Okay, this one. Pre-fault voltage is 525 kV. So 525 kV, the pre-fault voltage, you divide with the nominal voltage value, which is 525 divided by 500. So we have 1.050 degree. And then one thing you need to know, because we have to calculate the fault current in per unit. So you need to have this one, the base value. You need to calculate the base. So since that in the question, we know that S base for the complex power, V base times SI base. The V base we already knew from the given question, which is 500 kV. But remember one thing, because this is the three-phase. The three-phase means that square root 3. Square root 3 times the V base times the I base. So you need to manipulate this equation here. So we have I base equal to S base divided by square root 3 at the V base. And then we have the I base current, which means 1.155 ampere. And from here, we can find the per unit, right? Okay, the per unit, the I per unit is actually I actual divided by I actual divided by I base. But remember one thing, because we already determined the pre-fault voltage, which is 1.05. It means that you have to use the Ohm's law, which means IF per unit equal to V divided by Z Thevenin or H Thevenin. X Thevenin. So V equal to 1.05 here, the pre-fault voltage, 0 degree, divided by the value of the X Thevenin or Z Thevenin. So we have minus J 3.933 per unit, which means that 3.933 is in magnitude, minus 19 degree in angle. So we have this one, but remember one thing, that the question asks about the actual value. And of course, you need to do what? You need to find the IF in actual, which means that the I base here times the I fault in per unit. So we have the actual value for the current here. So please be careful when you read all the question in your final exam. Jaga-jaga awak kena berhati-hati, kena faham betul-betul. Okay, then for part C, determine contribution to the fault from generator 1 and from line 1, 2. It means that you can see here, this is actually in purple. Tak salah saya warna purple ni kot, purple color. Okay, this one. From generator 1 and from line 1 to 2. It means that from here, you need to find what? You need to find the current divider. Okay, using the current divider. So by using the current divider, which means that you need to find the IG1. IG1 is actually from here, we can see that from this one, the Z Thevenin here, we can see that this is the numerator part here. You can see that is this one, J0.4583 here. Divide by J0.4583 plus J0.64. Actually, when I try to calculate for this one, I refer back at this X Thevenin here or Z Thevenin here. Okay, and then if you want to make a clear vision on this current divider, you can draw it by yourself. You can draw how you can calculate for the IG1 and the I line 1 to 2, and then you can have the exact idea on how to use the current divider formula here. So basically, I already know. That's why I straightforward going to this one here. So this one might multiply with the I fault here. And then I have the answer is minus J 1.641 per unit. And again, because this one is per unit, I have to find the actual value, which means that I need to multiply with the I base here. When I multiply with I base, and then I can obtain the generator current in actual value here. And then again, I have to do for the I line 1 from bus 1 to the bus 2 in per unit. Again, I have to use the current divider again. So basically, I have to find the new value for the numerator, but denominator is the same value. And then I multiply with the I fault here. And then again, I have the different answer here, which means that the current flow from bus 1 to the bus 2, which is the transmission line. And then I have here different value here from the IG1 here. And of course, again, I have to multiply with the I base here. This one is I base. So I have this answer here, which means that the actual value for for the line current that flow from bus 1 to bus 2. So this is how you solve for question number 1 here in the tutorial 2 fault question. So this is how you draw. You can do it again. I think I want my student, especially in group 2, can have the idea on how to solve this kind of question. So after you already know about this concept here, then I want to go to the question number 2. Question number 2. Question number 2 is basically this one is same. If I'm not mistaken, this one is same as in the slide in PowerPoint, but this one is a different value from the slide in PowerPoint. I don't want to touch on this, but you need to remember one thing: you need to study, because as I mentioned before, the fault, especially if you want to calculate the fault current, you have two methods. Number one is network reduction method, which means that you have to apply the Thevenin theorem. Number two, you have to study the Z-bus algorithm, which means that you have to study the link, the element, and then the branch, all this kind of thing you need to study it again in order to find the Z-bus algorithm. This is very, very important. Sebab dalam fault, dia akan masuk dua benda ni. Fault question 1 and question 2 yang akan masuk. Just awak kena study balik lah. You have to study back again for question 1 and question 2. Try to do it again. And then I'm going to the wait. Okay. For question number 4, number 5. Okay, this one. Okay, this one cover the symmetrical component. Symmetrical component of a set of unbalanced three-phase current. Okay, when you see this kind of question, we can see that different magnitude, different angle. This is actually unbalanced. Okay, unbalanced three-phase current. Okay, now you have to what? To do what? You have to obtain the original unbalanced phasor, which means that you need to calculate for this one. You need to calculate the phase current A, the phase current B, and the phase current C. But the most important thing that you need to understand, you need to know is, you need to know this one, the basic equation in order to find the original phase, which means that the original phase current, the IA, IB, and IC. But remember one thing, we need to introduce the symmetrical component current, which are zero sequence, positive sequence, and negative sequence. So you need to add this one by using this standard formula here. So IABC equal to symmetrical component transformation matrix times the IA zero sequence, IA positive sequence, IA negative sequence. But this one you need to memorize. You need to memorize this one. Symmetrical component 1 A square A 1 A square, and then times this one IA zero sequence, IA positive sequence, IA negative sequence, and again you need to expand. You need to expand this matrix here 3 by 3 times 3 times 1. So from here we can get the value for IA. IA is actually IA zero sequence plus IA positive sequence plus IA negative sequence. So we have the answer as in slide here. And also this also goes to the IA IB, which means the phase current B. Okay, IA zero sequence plus A square. Okay, A square here, which means that equal to magnitude 1, degree is 240. But for the A here, operator A here, the magnitude is 1, the angle is 120 degree. This one you should be memorized. Awak kena ingat yang ni. This one is very, very important. Because this one you need to convert it into the original phase current. But you need to, another thing I need to stress, you need to introduce the symmetrical component current, which covers zero sequence, positive sequence, and negative sequence. Okay, from here we can get this answer here, and then again you have to find the phase current C here, IC, equal to IA zero sequence plus operator A times IA positive sequence plus A square, operator A square, times the IA negative sequence. So you have the answer here. So basically this is very simple, but you need to remember one thing. If the answer, if the question asks about, you need to find the symmetrical component current, which means that you have to find I0 sequence, positive sequence, and negative sequence. Okay, this matrix is actually will become matrix inverse, and then I, P, C. But this one is depend on the question. This one is very easy because you need to find the unbalanced vessel. We just use this formula here. But what if the question asks about symmetrical component current, which means that you need to manipulate this general equation here, so we become like this. Jadi awak kena baca soalan tu betul-betul lah, kena faham betul-betul lah. Okay, and then question 6. Okay, this is for the voltage. Okay, question 5, mostly on the current. Now we are focusing on the voltage. Okay, but for this one, okay, in this question, given that the voltage at phase A 230, 0 degree, 210, minus 110, 190, and 110. And then this question asks about determine the sequence component of the voltage. Which means that you have to do what? You have to determine the VA0 sequence, the VB0 sequence, the VC the 0 sequence, the VA positive sequence, the VB positive sequence, and VC positive sequence, and also VA negative sequence, VB negative sequence, and VC negative sequence. But again, okay, this is very, very basic formula. You need to know. Okay, it's a very basic formula. Okay, right now we want to find this one, V0 sequence, positive sequence, and negative sequence. It means that you must know the symmetrical component matrix A inverse. This is actually from here. All right, and then VABC you have to put in terms of the matrix form. Awak kena letak dalam bentuk matrix. And then we expand it. We expand this matrix form here. We can get VA0 sequence here, 1/3 VA plus VB plus VC. We just plug all this value because this one is given in the question, right? 230, 0 degree plus 210 minus 110 degree plus 190, 110. This one is given in the question. Just plug in the value, then straight away we can get the answer for the VA0 sequence. And again, if you need to find the VA positive sequence here, you need to refer at this matrix here, which means that 1/3 times the VA plus A, operator A, times the VB plus operator A squared times the VC. So from here, just plug in on the value, and remember one thing, A here is equal to 120 degree, A squared equal to 240 degree. Okay, by using your scientific calculator, you can get this answer for VA positive sequence. And then for VA negative sequence, again, from this matrix here, you can get 1/3 VA plus A square VB plus A times the VC. And then again, we have to insert all the respective value for VA, VB, VC. And again, A square, you have to know that the value, the standard value for A, operator A, and operator A square. And then we can get as this answer here for the VA negative sequence. And again, of course, we need to find the V0 sequence, positive sequence, and again for negative sequence. But the main thing is, before you find the VA0 sequence, we need to find also the VB0 sequence, which means that the VB0 sequence, this one, is equal to the VA0 sequence. VC 0 sequence is equal also to the VA 0 sequence. So this is actually coming from, sorry, this is actually coming from this one, the VB 0 sequence here. The VB 0 sequence equal to VA 0 sequence. And for a VB positive sequence, the VB positive sequence equal to A square VA positive sequence. VB negative sequence equal to A operator A times the VA positive sequence. So from this standard formula here for the VB and VC, I can obtain for VB 0 sequence, VC 0 sequence, VB positive sequence, VC positive sequence, and VB negative sequence, and lastly the VC negative sequence. Just plug in the value so you can get the answer as in slide here. So this is basically the basic calculation for current for question 5 and for the voltage for question 6. But the main important thing is you need to know this one. You need to know the basic equation here, the general equation here. If you not remember this one, and then it will become a big problem. Nanti saya tahu sebab apa. Okay, sini mana tadi tu? This one. This one. So very important. Okay, then stop here for this one. Then going back to the okay, question number 7. Given that the reactant data in per unit, you can see here the component of power system network, we have generator 1 and generator 2 respectively, and also we have transformer 1 and transformer 2 respectively, and then we have the transmission line that connected from bus 1 to the bus 2. And from this table also, we can see that we have the reactance value for positive sequence here, positive sequence, negative sequence, and also for the 0 sequence. And then you can notice that the value of positive reactance and positive sequence and negative sequence reactance have the same value for all components in the power system network. But for the 0 sequence, we have a totally different value for generator 1, generator 2, and transmission line going to the transformer 2, except that we have the same value for transformer 1 and transformer 2 for 0 sequence reactors. It's also similar for the reactors of positive sequence and also for the negative sequence. Basically, in this question, it asks about how to draw the positive sequence, the negative sequence, and 0 sequence. This is the pattern question. If the question asks on how to solve the fourth question regarding on the symmetrical fault and also for the unsymmetrical fault. Okay, we can see that the first thing you need to do is you need to draw. How to draw this one? Okay, this is basically the question. Then again you can see that all the components in this power system network, you can see that this is generator. We have the star connected to the ground, and also at the primary side of transformer 1, you can see that this is delta connection. For secondary is star connected to the ground. For the secondary of transformer 2 is star connected to the ground, and the primary of the transformer 2 here, we can see that this is actually in delta connection. And for generator 2, which is similar for generator 1, we have the star connected to the ground. So right now, I want to show on how to draw or sketch the positive, negative, and zero sequence network. So this is how you draw. You draw the positive sequence. The basic thing that you need to know, we must have the voltage source here for generator 1, and then we have the reactance of generator 1. This is how you model your generator. If you want to draw for the positive sequence, you must have the voltage source, and then the series with the reactance of generator 1. And of course, we have we have the transformer component that connected from the bus 3 to the bus 1. This value here, actually I refer back at this table here, according to this positive sequence here. And then we have the transformer 1 here, J0.25. And of course, we have the transmission line here, J0.3. Transformer 2 here, J0.25. And then we have the reactance of generator 2, J0.1 per unit. Okay, this is how you draw the positive sequence network. So remember, this is actually connected to the ground. Connected to the ground, and this one connected to the ground. How to draw the negative sequence? We just remove the voltage source for generator 1 and also the voltage source for generator 2. Awak buang dia. Just copy back all this positive sequence, but you remove all the voltage source. Awak cuma remove ni. Awak buang ni, generator 1 generator 2 voltage source. Jadi dia akan dapat macam ni lah, the negative sequence here. So this is negative sequence network. But the most important thing, if you want to draw for the zero sequence, you need to take a look back at your single line diagram. Because for zero sequence network, you must consider all these connection here. Star connected to ground, delta here, star connected to ground. You must consider. So how to draw? Okay, how to draw? Okay, we start from here, from generator here. Okay, again, for zero sequence, similar as in negative sequence, we don't have the voltage source. The voltage source only exists for positive sequence only. Okay, awak kena faham. Voltage source hanya wujud pada positive sequence. And then zero sequence here, okay, this one, the value is actually I refer back to the table. I have J0.05 per unit. And then going to this one, okay, transformer. Because this one I know, at the primary side of the transformer 1, we have the delta here. When we draw the delta, which means that this one you open. You open here, because this is actually belong to the delta. And then this one you connected to the ground here. And then this is the reactance of transformer 1. And then for this one, the secondary side of transformer 1, because this one I know that the connection is actually star and then connected to the ground. So this is the reason why we have the straight line here for the secondary of transformer 1. And then going to this one, this is line, transmission line, okay, that connected from bus 1 to the bus 2, just straight line. We have the reactance here, J0.5 per unit. You need to refer back to the table. And for this one, we have the transformer 2 here. Okay, this one is actually the star connected to the ground. So this is the reason why this one is become straight line here. That connected from bus 2 connected to the transformer 2 here. Okay, for the primary side here, the primary side of transformer 2, this one is delta. This is how you draw. You leave it blank here. Do not draw straight line here. So this is, if you draw straight line here, your answer will be false. Okay, jawapan awak akan salah. Sebab this one is actually the delta. It should be, leave it blank here. And then this one is XG2, which means that the reactance of generator 2. Okay, this is how you draw for positive sequence, negative sequence, and zero sequence. hopefully you can understand. Saya harap sangat awak semua faham lah macam mana nak lukis kan, how to draw this sequence network. Okay, then for question number 2, you need to determine the Thevenin sequence impedance for the fault at bus 1. Okay, it means that you have to draw. You have to draw here. The fault occurs at bus 1 here. Okay, which means that you copy back your sketch on positive sequence, but you need to show how which one is the fault occurs, which bus. Okay, you show here or at bus 1 here. Means that this reactance of generator 1, we can add it together with the reactance of transformer 2 because this is actually in series. It's not in parallel. This is what I'm get from your senior student. Your senior student, they assume that a bus here is actually parallel. No, that's what is totally wrong. Totally wrong understanding of the concept of the sequence network. No, it cannot be parallel. This one is actually in series. So this one, J0.1, you need to add together with the reactance of transformer 1 here. But for this one, this is actually in parallel because the fault occurs at bus 1. It means that you have an obstacle there. So parallel, this one J0.3 plus J0.25 plus J0.1. This one will become in series. So we have here J0.35 per unit parallel with J0.65 per unit. You solve this one, then you have J0.227 per unit. Okay. I did write this one, Z1 here. It's actually Z superscript here, which means that this is belong to the positive sequence. Some of the reference books, or even in textbooks, they tend to write like this, Z superscript 1. Or some of the reference book, the author write like this, Z subscript 1, which means that this is actually the same. Dia sama aja, tapi different interpreting of the symbol of the abbreviation. Dia sebenarnya sama aja, tak ada apa pun. Tapi kalau awak tulis macam ni pun okay. If you write like this okay, I accept it. If you write like this one, it's okay. Okay, mana-mana pun tak apa, okay je. Okay, the most important thing you need to know lah. We need to know from the question, the fault occurs at which bus? Fault occur kat mana? Jadi kat situ awak kena tahulah. Okay, this is how you solve it. And then for negative sequence, this one become very easy because we know that Z positive sequence equal to Z negative sequence is equal to the same value. This is very simple. We just draw back the negative sequence, but without the voltage source. We remove the voltage source, but this one is Z1 equal to Z2 equal to this value here. This one is very easy. Okay, zero sequence. But for zero sequence, you just copy back your sketch on zero sequence. But remember one thing. This is I need to stress this one because some of students did a careless mistake. If you want to find the zero sequence impedance, you have to stand here. Imagine that you stand here. When you stand here, this one is open, right? Because this one is open, when this one is delta connection, we cannot include this one. This one is cannot include. You remove this one. You standing here, you see means that you only see from here going to here. This one we cannot include because this one is already open, right? So we just consider this one, which means that J0.25 here, because the fault occurs at bus 1, which means that parallel. J0.5, we add together with this one because this is actually in series. So then we have the answer here. So I want all of you to be careful, especially on this part, zero sequence. Jadi memang saya nampak banyak student dia tak faham. Dia ataupun yang kata lain kalau mistake lah. Ini memang saya nampak selalu dah. Dia tak nampak kat mana saya kena duduk. Dia at least I'm saying that I made I want you all of you to imagine. Let's say that you're standing here, and then you see on your right hand side, you only see this one. This one cannot be included. This one cannot be included. Okay, all right. Okay, this one for zero sequence. Okay, this one. Okay. Okay, for part 3. Part 3, okay. You compute the fault current in per unit for the fault at bus 1 for different type of fault, which are, okay, this one, single line to ground fault, line to line fault, and double line to ground fault. Which means that it covers all the 3 types of the unsymmetrical fault. And then all types of the fault are true fault impedance, which the fault impedance equal to J0.05 per unit. Assume that the generator electromotive force of generators equal to 1.05 per unit, which means that you need to know you need to know the formula. Without the formula, you cannot solve this question. So from the given question in part 3, which means that we already know that the fault impedance, this value, and then for the electromotive force internal generator of the voltage is 1.05 per unit. Just plug in the value here. You substitute all this value here according to the SLG fault here, and then you divide with positive sequence-impedance, negative sequence-impedance, zero sequence-impedance that you calculated earlier in part 2 Roman, plus 3 times ZF, which means that J0.05 here. So we have the answer like this, minus J3.9748 per unit. And then for line to line fault, this is the basic formula here. But you need to understand first, if you want to find the fault current for SLG fault, always remember and always know that the answer should be in minus J. In minus J. But the fault current for line to line fault, we have the exact value, which means that we don't have the imaginary part. Okay, I hope that my explanation you can understand. You can differentiate between the answer for SLG fault and also for the line to line fault. So for the line to line fault, according to the basic formula, minus J square root 3 IA positive sequence magnitude. So basically, this one, you have to find this one first, IA positive sequence, which means that IA positive sequence equal to EA times the positive sequence impedance plus negative sequence impedance plus the fault impedance. So from here, we already calculated from the part 2 Roman, the value here, and then plus the fault impedance here, and then we have the answer here, and then we just substitute into IA positive sequence here, and we have the answer here, which is in the exact value, which means the real number, minus 3.6013 per unit. Always careful, always remember that the value cannot be in imaginary for line to line fault. But for SLD, yes, we can have the answer in imaginary value. Itu cara awak beza. This is how you differentiate between the value, the final answer for SLG fault and line to line fault. But the trickiest part, this one, the double line to ground fault. Okay, why I'm saying it's trickiest part? Because the simple formula in order to find the LG fault, which I4 equal to IB plus IC. Okay, we can say that this is simple, right? But you need to find what? You need to find the IB first. You need to find the IC. But how? And then you can use all this formula here, IA positive sequence, IA zero sequence, IA negative sequence, which is very, very long. This is where the careless mistake come. I know this one. Kalau dalam DLG ni memang saya akan nampak. Kat sini lah selalu yang akan datang yang careless mistake. Okay, this one. Don't be panic about all this thing. You know, You don't need to memorize. You just understand the question. You just know how to use the formula. Itu saja cara dia. Tapi kalau awak tak tahu cara nak guna dia, problem jugalah. And then again, but another thing that for arithmetical form, of course, we need to introduce the zero sequence, positive sequence, and negative sequence. This is why you need to remember this standard formula here. I A B C equal to matrix A symmetrical component transformation time I zero sequence, positive sequence, and negative sequence. Just plug in all the value here, and then we have the answer like this one. And then this is this is the IB, and then this is the IC. This one is IA, IB, and then this one is IC. So in order to find the fault current for DLG fault, double line to ground fault, IB plus IC, which means that IB here plus IC, and then we have the answer here. Okay. This is for DLG fault. I know this is very long, but the most important thing you need to be cool. You need to be careful, and then try to reduce your careless mistake, especially on this DLG fault. Okay, and then for this one is according to the matrix SLG fault at bus 1. Okay, going back to the question. Okay, this one. Given the positive, negative sequence bus impedance, this one, we have the 4x4 matrix. Okay, Z11, Z12, Z13, Z14 until Z44 here. And then we have the zero sequence impedance in matrix form. Z11, Z12, Z21, Z22. Okay, the question is aborted incident that the fault impedance equal to 0. And then we have the single line to ground fault occurs at bus 1. Using the given sequence impedance, which is cover this matrix here, 4x4, and this one 2x2, determine the fault current and the three-phase bus voltage during the fault. Assume that all pre-fault, which means that before the fault occurs, the bus voltage equal to 1.0 per unit. Okay, for this one, you need to refer this matrix here for the positive sequence, negative sequence, and zero sequence bus impedance. Okay, how to solve this one? Okay, this one we know that from the given question, SLG, single line to ground fault, which means that you need to memorize, or you need to refer the basic formula for single line to ground fault. So for the single line to ground fault, the basic formula is IK, which means that the K here is actually referring to number of bus. IK zero sequence equal to IK positive sequence equal to IK negative sequence equal to VK0, which means that this is the pre-fault voltage. Pre-fault voltage. Okay, pre-fault voltage. This one ZKK. Okay, let's say that you have K equal to 1, bus 1, which means that Z11, 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 which means that Z11 positive sequence, Z11 negative sequence, Z11 zero sequence plus 3 times ZF. So how to find the value for Z11, Z22, Z11, zero sequence, negative sequence, and positive sequence? You just refer back that from your previous calculation, you can get the answer is J0.2275. It's actually from here. This one here. Negative sequence, and also for positive sequence. Then plus the zero sequence, which means that J0.1875 plus 3 times the fault impedance, which is the bolted fault here, ZF. So we have the answer is this one. Okay, then of course we have to find the the current, the phase A, phase B, and the phase C by using this standard formula here. Okay, then just plug in all the value here. So we have the value is minus J4.6692. So this one is become a 0. You need to expand. You need to expand this matrix here. So in order to get the answer here. So then after you find the fault current, and remember one thing, because in the question also asked about fault current and the three-phase bus voltage during the fault condition. Three-phase bus voltage. This one. So the bus voltage formula, okay, this one, VI0 sequence during fault, VI positive sequence during fault, VI negative sequence during fault. Okay, this is the formula. As in the formula also, you can see that in positive sequence, we have only the voltage source. This one is correct because according to the, when you draw the positive sequence impedance, we only the voltage source only exists on the positive sequence. So this is the reason why from this equation we can see that there is no voltage source, which means that there is no voltage source exists on zero sequence impedance, which is 0. And also for negative sequence impedance, we have a 0 here. So from here again, we have to find the voltage at phase A, phase B, and phase C by using the standard formula here. And then we solve it in terms of this matrix form here. We can see that the V1, zero sequence, positive sequence, and negative sequence, well, this is actually from here. From here, I can know that I need to find the voltage at bus 1, the voltage at bus 2, the voltage at bus 3. So here, I write like this: V1, zero sequence, positive sequence, and negative sequence. And also I write like this. Then I know that from the previous calculation, I obtained all these zero sequence, positive sequence, and negative sequence. I have all this value, and then I have which is this answer here. And then for the bus 2, the fault at bus 1, I have this answer here. So I can get this answer. And then for the bus 3, the fault at bus 1, I have this kind of answer. So when I compare between the voltage at bus 1, the voltage at bus 2, and then the voltage at bus 3 for zero sequence, positive sequence, and negative sequence, we can have a different value. We can have the different value, and then we know that actually when the fault occurs at bus 1, this one, bus 1 here, we can see that the voltage at bus 1 is smaller. It's smaller than the voltage at bus 2 and also at the voltage at bus 3, which means that when the fault occurs at bus 1, the current will become high and the voltage will become it will reduce until going approximately equal to 0. Jadi bila awak compare tengok a voltage at bus 1 here, the voltage at bus 2 here, and the voltage at bus 3 here, we can say that the voltage at bus 1 is smaller than the other bus, which means that the fault current must be higher when the fault occurs at bus 1. Jadi bila awak tengok ni, awak akan nampak lah, sepatutnya nilai voltage kat sini dia lebih rendah kalau compare dengan voltage dekat bus 2 dan juga bus 3. Ini cara awak nak check jawapan awak betul ataupun tak. Itu cara dia. Jangan main kira aja, main kira saja berat sampai tak faham apa, tu susah juga tu. Okay, then first one. Of course, when you find for the zero sequence, positive sequence, and negative sequence, the last one, okay, the last one you have to find the voltage at bus 1, the voltage at bus 2, and the voltage at bus 3 by using this standard formula here. This one. The symmetrical component transformation matrix A here, time with zero sequence, positive sequence, negative sequence, and then we have this kind of answer here. Okay, hopefully you can do it again for question like this one. Wait, check again. Okay, this one is very important. Wait, I need to take a break around 2 or 3 minutes. Then we continue with this solution here. Question number 8. Okay, for question 8, given that we have step up transformer here, transformer 1, transformer 2, then we have the upper line here, which is line 1, the lower line here, which is the line 2, which is parallel, line 1 parallel with line 2. And of course, from the given question, we know that the fault occurs at bus 1 here. And another thing that you need to see is the difference between the connection from transformer 1, transformer 2, and generator 2 and generator 1. Okay, from here. At the generator 1 here, we can see that we have the neutral reactance here. Okay, we can see that this is the difference between generator 1 and generator 2. So we have the neutral reactance here. So this is basically typically data given in table 3 here, typically data for all the components in the power system network. So we have the positive sequence, negative sequence, and also the zero sequence here. So from here, we can see that we have the reactance Xn. Okay, this is the value. So you need to obtain the Thevenin sequence impedance for the fault at bus 1 and compute the fault current per unit for the following fault, which means that you have to find a bolted 3-phase fault at bus 1, SLG fault at bus 1 with the fault impedance this one, a bolted line-to-line fault at bus 1, bolted means that fault impedance equal to 0. DLG fault at bus 1 with the fault impedance ZF equal to J0.1 per unit. So this is how you find. And again, I think I don't want to repeat again. For the positive sequence, you must have this one. water source. Then we have the reactors of generator, the reactors of step-up transformer, transmission line, SL line 1, SL line 2. This one is step-up transformer 2, and then we have the reactors of generator 2. Then again, we have to find the positive sequence impedance. So this one is in series. This one is series, parallel, because the fault occurs here, parallel. This one is parallel, J0.25 per unit, parallel with J0.25 per unit. And then we need to add together because this one is series, right? Series plus J0.255 plus J0.15. So you simplify this one. So you have the positive sequence impedance, J0.2334 per unit. Okay, then for the sequence, very simple. Remove this one, remove this one. So we have Z2, which means that Z negative sequence impedance equal to positive sequence impedance equal the same value here. Okay, then for zero sequence impedance, okay, for this one, need to remember one thing because we have the neutral impedance. When we have the neutral impedance, which means that we need to consider the connection type here. The neutral impedance at the generator 1 here. So this means that you need to consider this type of connection at generator 1. The neutral reactance, you need to multiply with 3. 3 times neutral impedance, 3 times J0.05, we have J0.15 here. So again, this one, the reactors of generator 1. This is the transformer 1 here. For transformer 1, again, we need to consider the type of connection. This one is for delta. This one is open. This one is secondary side of transformer 1. So star connected to the ground, straight line. Then this one is parallel line. This one will become delta here. This one is secondary of transformer 1, transformer 2. This is primary of transformer 1. Then this one is reactors of generator 2. So from here, okay, this one J0.15 here, you add together because this one is series. So we have J0.255. But this one you need to remember one thing because zero sequence we neglect this one because this one is open, right? So we start from here. We take a look at here. This one. Zero sequence impedance, not from this one. Tadi saya nak testing lah, tengok kamu semua alert ataupun tak. Just this one is we neglect it. We just starting from here, zero sequence impedance. So this one J0.255 parallel, because the fault is occur here, parallel J0.55 parallel with J0.45 plus J0.255. This one we neglect. We remove it because this one is open, right? Open. So the zero sequence impedance is equal to this value here. Okay, then for the fault current, a bolted 3-phase fault at bus 1. Okay, this one, 1 over J0.233 plus 0. The fault impedance equal to 0. The pre-fault voltage equal to 1. So Z1 is actually according to this 0.2334. Okay, saya tertinggal.
Tuan.
Ya.
Kenapa kita kena add SZN dekat zero sequence saja?
Sini 3ZN ni
kenapa tak dekat sequence lain? Saya nak tanya tu saja.
Sebab bagus soalan tu. Sebab sini neutral reactor dia ada, sebab dalam zero sequence kita kena consider ni. Kita kena consider semua dia punya type of connection. Jadi in generator 1 which consists of neutral reactor, you must times with 3. You must time with 3. Ini memang dia punya rule dia. You must time with 3. So this is reason why you need to write 3 times J0.05. Because in zero sequence, you must consider all the type connection for generator, for transformer and so on. Awak kena ambil kira. Sebab tu kita kena ni. Bagus soalan tu. Saya suka soalan tu. Okay, bagus kan? J0.15. So, okay, hopefully my explanation clear on that. And then in order to find the fault current for the bolted three-phase fault, so this is the answer here. And then for the SLG fault at bus 1, by using the standard formula here for the SLG fault, so just plug in all the value here. So you have the answer is like this. There for the bolted line-to-line fault at bus 1. Okay, remember one thing. The fault current for line-to-line fault minus J square root 3 IA per city sequence. IA per city sequence is according to this formula here. So you have to find this one. So you have the answer like this. Nampak tak perbezaan dia? Bila kita nak calculate between SLG and line-to-line fault, SLG always we have minus J tau. Faham tak? Awak kena tahu ni semua benda ni. SLG, bila line-to-line fault, kita akan dapat tak ada benda imaginary value. Itu perbezaan the difference value, the final answer for SLG and line-to-line fault. Kalau awak dapat, katalah awak dapat fault untuk line-to-line fault ni, awak dapat minus J. Awak cepat-cepat tengoklah kat mana awak silap. Adalah silap kat mana-mana. Tiba-tiba kat sini IF SLG fault, tiba-tiba awak dapat real value, tak ada imaginary. Ada silap kat mana tu. Cari cepat-cepat. Okay, then this one, the LG fault is very long. Because you need to remember all these things. All this formula, IA positive sequence, IA zero sequence, and IA negative sequence. And again, it's actually the simple formula for DLG. I4 equal to IB plus C. Of course, it's very simple, but you need to find this one, IB and C. Okay, how to find IB and C? You have to use this formula here. Itu yang dipanjang tu. IABC equal to matrix A times I0 sequence, positive sequence and negative sequence. Awak kena buat ni. Itu yang dia panjang. Itu yang jadi macam student tak boleh terima ni, DLG ni. Sebab dia panjang. Tapi itulah, we have to be very careful lah when you plug in all the value. Okay. Okay, I stop here. Because I want to go to the stability part. Okay, any question? By the way, your friend, tadi kawan awak tanya soalan tu bagus tu. Okay, saya nak masuk stability sebab kita tengok masa pun dah tak mengizinkan. Stability. Okay, for stability, actually I already discussed with group 2 student. Question 1, I think this was very basic. Just no need to take a look. For question 2, okay, for question 2. For question 2, okay, for question 2, okay. Given that the single line diagram of a three-phase, we have 60 Hz synchronous generator connected through a transformer and parallel transmission line to an infinite bus. All reactors are given in per unit or common system base. If the infinite bus receives 1.0 per unit real power, which means that P equal to 1.0, power factor equal to 0.95, power factor lagging. So you need to find the part A, the internal voltage of the generator. You have to find the E prime. And then you have to find the equation for electrical power delivered by generator versus its power angle for pre-fault, during fault, and post-fault if the fault occur at bus 3. Okay, for this kind of question, if you have, if the given figure 1 here, you will need to draw back. Cara dia, awak kena lukis balik, bawah awak akan nampak. You have to draw back in the simple form, which means that in the per unit form. So we have the generator side, which consists of the voltage source in series with the reactance of generator. So we have J0.3, and then we need to draw the reactance of transformer J0.1. And then we have the bus 1 to bus 2, J0.2, bus 1 to bus 3, J0.1, bus 3 to bus 2, J0.2, and then we have the infinite bus here. Infinite bus voltage, which is equal to 1.0 per unit. This one is actually assumption value. Jika tak diberi pun dalam soalan, tak dimention pun 1.0, awak kena assume. We have to assume the V bus is equal to 1.0 volt. Awak kena assume dia. Then we know that from the given question, power factor is equal to 0.95, and then the real power is equal to 1.0, right? So again, you have to find what? You have to find the theta, okay, the angle. So from here, we know that power factor equal to cos theta, theta equal to cos inverse 0.95. So we can obtain the answer is 18.20 degree. And of course, you need to know the power triangle. And then from the power triangle, we can get the S equal to P times the power factor, which means that you have to, if you, saya tak pastilah berapa orang boleh ingat ni power triangle ni. Power triangle, if you can remember, power triangle, P, and then this one is Q, and then we have theta here. This one is perpendicular 90 degree. Okay, this one is P. Oh, sorry. This one is P. This one is Q. This one is S, apparent power. It means that if you expand S equal to VI, which is the complex power, if we expand it, we can get S equal to, in terms of the active power and in terms of the reactive power. So we have S equal to P plus JQ, because we know that the cos theta is equal to power factor. The cos theta, which means that cos theta, which means that the sekejap. Betul lah. Q equal to cos theta equal to power factor, right? Power factor, then cos theta what? Cos theta is equal to P over S. P over S is equal to power factor, which means that we need to find the S is equal to P times P divided by power factor. So that's why S equal to P divided by power factor. So 1 divided by 0.95. So we have the value in magnitude 1.0526. The angle is 18.20 degree. And then from here, we need to find the current, right? I equal to S conjugate divided by V bus conjugate. So we have the answer here is the magnitude is 1.0526 minus 18.20 degree per unit. Okay. And then we have to find what? We have to find the voltage, right? The voltage behind transient reactance. So in order to find the voltage behind transient reactance, which means that we need to find the E prime. We need to find first the XT, which is the transfer reactance. So XT is equal to this one in series here. In series, the plus with this one. This one is parallel with this one. This one in series. And then we can get the value is J0.52 per unit for the XT. But again, you need to know the equation for internal transient voltage, which means that this one is the V bus infinity plus J XT transfer reactance times the I, the current. So this is actually the equation here come from here. come from this model here. This one is X, D. This one is, we have the voltage source here, which means that E prime. This one is B bus infinity. Okay, this is the current. So this is how you can get the equation here. Actually, from this figure here, after you simplify the circuit, from here you can get this equation here. So after you find the E prime here, so we have the answer like this. So again, for the part B, you need to calculate the power angle equation. The power equation, but you need to remember one thing, because we need to consider three conditions here. Number one, we need to consider the P-fault. The P-fault means that before the fault occurs, the P-fault. Okay, some of the students, they tend to write like this, P0. 0 here means that pre-fault. Some of the students, they tend to do like this, P1 equal to pre-fault. P2 during fault. Dia sebenarnya tak salah pun, mana-mana boleh. Ada setengah student, dia selesa pakai P0 tau. P0 sama pre-fault, P1 during fault, P2 after fault, post fault. Mana-mana pun okey je. P3 post fault. Tapi terpulang lah, sebab dia tak salah pun, tapi pastikan dia betul lah kamu tulis tu kan. Post fault. Ada setengah student dia pakai P0, P1, P2, mana-mana lah. Okey je, asalkan dia betul lah. Asalkan betul dia punya sequence tu betul lah. So P-fault, P0 E prime magnitude times the V bus magnitude divided by XT, assign rotor angle. So rotor angle. Always remember, in order to find the power angle equation, we know that the rotor angle at x-axis, the power angle as y-axis, and then we have to draw the sine waveform, which means that starting from 0 until pi here, which means pi radian equal to 180 degree. And then we have the in the middle here, which means that pi over 2, which means that 90 degree. Okay, this is the maximum power here, P max. This is the power angle curve. Okay, then from here we can get the pre-fault power. The pre-fault power, we know that the E prime here 1.2812, the V bus equal to the given equation 1.0 divided by the transfer reactance 0.52 sine rotor angle. So we have the power angle for the pre-fault condition 2.4638 sine rotor angle. Basically, most of students can calculate for this pre-fault power, but the problem comes here. The problem comes from here during the fault. Okay, during the fault occur at bus 3. When the fault occur at bus 3 here, which means that this is actually connected to the ground. When this one is connected to the ground, which means that you only consider this reactant, and also this reactance here. This one we cannot go, because this one is actually the current, the flow from generator here is going to the bus 1 and then going to the bus 2 and then going to the supply to the V infinity here. But for this one, for the lower line, which means that going to the bus 1, going to the bus 3 and then going to the fault. We are going to the, sorry, not to the fault, going to the ground. But it cannot go to this one, because the fault occurs here at bus 3. It cannot go to the J0.2 here, which means that the line that connected from bus 3 to the bus 2. Dia takkan lalu sini. So right now we can see that if you flip this figure here, nampak tak? If you flip this figure here, we can see that this is actually the Y, the Y connection. Nampak tak? Ya. Y connection, nampak? Nampak betul Y kan? Y connection. So, okay, right now, if you want, you can see the Y connection here because I want to find. Actually, I want to find this one. I want to find the transfer reactors at this top here, which means that I want to find the reactors that connected starting from this side here, starting from reactor going to the bus 1 to the bus 2. If I want to find the reactors here, it means that I need to convert. I need to convert the star or Y connection to the delta connection. So this is how I draw it. Okay, I draw it. When I draw here, I know that J0.4 here, this one is coming from J0.3 plus J0.1, which means that J0.4 lah. And then I know that this one from bus 1 here to the bus 2 here is actually J0.2. And then I have the RC here, which means that from bus 1 going to the bus 3 here. So I have J0.1 here. And now I want to find this one. I want to find the connection, the resistance, the transfer reactance that connected from bus 1, not bus 1, sorry. The let's say I define this one as S here. S going to the bus 2 here. So in order to find this one, I need to convert from star to the delta connection, which means that I need to find this one. So in order to find this one, I label it as RAB. Okay, I label it as RAB because I define J0.4 here is RA, J0.2 here as RB, J0.1 here I label is RC. And then I know that from the basic formula, if you want to convert from star to delta, which means that I need to use this formula here, RAB equal to RA times RB plus RB times RC plus RC times RA divided by RC. Okay, from here, I solve it. Okay, I solve it. So I have this kind of answer here. So I have J equal to 1.40 per unit. But this one is very simple. This one is very simple. If you want to use my formula here, you can use my formula here. This formula here. You can use this one in order to find the XT here. You can obtain the similar answer. Awak akan dapat jawapan sama. J 1.4 per unit. So after you find the XT here during the fault, J 1.40, and then you have to write again P1. P1 here is means that during the fault. So E prime time V bus. Okay, this was basically the basic formula which is similar as during pre-fault. So I just plug in on the value 1.2812 times 1.0 divided by 1.4 sine rotor angle. So I have 0.9151 sine rotor angle. Okay, right now I want to make sure my answer is correct. Okay, you just compare. You just compare the power angle equation before pre-fault and during fault condition. We can see that the power magnitude is reduced, right? It's reduced from 2.4638 going to 0.951 per unit. Nampak tak? Dia turun kan? Dia reduce. Let's say if you answer bigger than 2.4638, it means that you already making a mistake when you convert from star to delta connection. Kalau awak dapat lebih besar P1 ni daripada P0 ni, maksudnya awak dah salah. Awak dah salah something dekat bila awak convert daripada star kepada data. So awak kena berhati-hati. Check balik. Awak jangan main terima je. Jangan main terima je, tak ada. Awak kena faham konsep dia. Sebelum berlakunya fault, memang dia tinggi power dia. Tapi bila berlakunya fault, dia akan reduce. Tu konsep dia. Dia akan reduce. Dia tak mestinya akan lebih besar lagi nilai dia. Daripada 2.4638. Dia akan kurang. Dia awak kena check balik lah kat mana calculation yang awak buat silap. Jangan main terima je. Jangan kata, okay jawapan aku. Tak. Something wrong lah. And then post-fault. Post-fault is very, very easy. Post-fault, why I say very, very easy? Because let's say we have a circuit breaker here, right? When the fault occurs here, we need protection system. When the fault occurs here, the breaker here is actually in closed state condition. Fault berlaku dekat bus 3. Fault occurs at bus 3, which means that CT, breaker and relay function together. So when the fault occurs, so the relay sense the fault and it will give signal to the circuit breaker, and then the circuit breaker here will be open. When the breaker is open, which means that this one is open. You need to draw like this for the post-fault condition. Post-fault means that when you want to clear the fault or you want to isolate the fault, the breaker open. When the breaker open, it means that the current cannot flow to this one. The current is follow from here, going to bus 1 to the bus 2 here. And then going to the infinite bus voltage. So this was very easy. You just find the transfer reactance, total reactance J0.3 plus J0.1 plus J0.2. So you have J0.6 per unit. And then again, you have to find the power angle equation for the post-fault, which means the P2. Okay, P2. Kalau awak tak P3 pun boleh, tapi awak buatlah macam mana pun, P0, P1, P2, ataupun P1, P2, P3, mana-mana pun okey je. Asalkan betul lah sequence dia tu. And then, okay, alright. From here, you just plug in on the value, divide by 0.6, and then we have 2.1353 sine rectangle. Then, when we compare, okay, then you need to draw this one. You need to draw the power angle curve. When you draw the power angle curve, we can see that during the post-fault, the magnitude is in between during fault and before the fault occurs, which means that the pre-fault or in steady state. SS here means steady state condition before the fault occurs or the pre-fault. Okay. Kalau awak kena make sure post-fault awak ni in between. Kalau awak dapat lebih ni, berarti awak dah buat silap. Mostly the mistake come from here. The mistake come from here during fault. This is the where I noticed that some students are struggle when doing the conversion from star to delta. Ini yang saya nampak ketara lah. Kalau dia tak betul sini, dia punya power angle equation totally wrong. Saya akan nampak. I can see your mistake. When if you have the answer like this, which means that the post-fault value before, the post-fault value between the pre-fault and during fault, which means that your answer is correct, totally correct. Tapi kalau awak dapat berbeza daripada sini, saya dah tahu lah awak dah buat silap dekat during fault condition. Okay. Alright, and then I'm going, I jump question 3, ada want to discuss question 3. Question 3, I jump to no, question 4 no. Question 4. Question sheet, no. No. It's fine. Question 8. Okay, for question 8, let me take a break about 2 minutes, then I will continue with this one. Question 8. Okay, for question 8. Okay, we have 3 phase fault occurred in the middle of this transmission line. And then we have initial constant, which means that the kinetic energy stored in the rotor, 5 megajoule per MVA at rated speed. And we have the transient reactant, XD prime, J0.22 per unit. And also we have the real power, which means that the P equal to 1.0 per unit to an infinite bus bar, which means this one. The protection system clear the fault and the affected line is open for continuation of operation. However, the system clearing time needs to be shortened by 75%. Analyze the initial system and propose the solution of a new clearing time and corresponding to the new rotor clearing angle. Assume that the power of the motor PM is equal to 0.8 per unit. Okay. How to solve this question? Okay, again, I want all of you to draw again. It means that you need to draw this one. Jangan salin soalan balik. Dah. Just extract from the given question what is the value given in the question. Awak extract balik. Bukannya salin soalan. Tak. Kalau awak salin soalan, melata awak tak faham langsung. H initial constant equal to 5 megajoule per MVA. Fault occur at the middle line of the transmission line. Generator delivering real power 1.0 per unit. Motor power PM 0.8 per unit. And then to shorten the clearing time by my score is wrong, 75%. And the proposed respective regulating angle is delta CR. So again, you have to draw again in terms of the per unit and the symbol of the reactance. And from here, we can see that this is the complete for the pre-fault analysis. Again, you have to write the power angle equation, which means that P equal to E magnitude times the V magnitude times the X magnitude sine rotor angle. Okay, then from here, we have to find, from the figure, we know that the E prime, which means that 1.25. So just plug in the value, 1.25. And then we have V infinity equal to 1.0. Okay, and again, we have to find the transfer reactant or the total reactant here, X here. So X here, from X here, we know that this is in series. Okay, 0.22 plus 0.36, and then plus this with this one, parallel with this one. So we have J0.22 plus J0.36 plus J0.72 parallel with J0.72. So we have J0.94 per unit. And again, we have to substitute X value here going to the power angle equation here. So we have 1.329 sine rotor angle. Okay. Again. Okay, for this one. Okay, remember one thing. During the fault analysis, we need to do the conversion for star to delta connection because this is actually in Y. Okay, how to divide this one? Because I know that the fault occurs at J0.4 in the middle of this transmission line, the lower transmission line here. So I divide into half, which means that J0.4 divide by 2. So, or multiply with half. So I have J0.2. So this is the reason why when I draw this one, I have this one is connected to the ground. When this one is connected to the ground, I flip this is actually Y connection. And then when I flip it, I have RA here is actually J0.58, which means this one. J0.22, J0.36. Okay, this is RA. And then for RB this one, J0.16 plus J0.4 plus J0.16. So I have here RB. And then I have the RC, which means that J0.16 plus J0.2. So this is RC. And now I want to convert into delta. When I want to convert into delta, it means that I need to find this one only, RAB here, which is in the top here. I need to find the RAB. So from here, I need to use this standard formula here, RAB equal to RA RB plus RB RC plus RC RA divided by RC. So this one I already write it, RA here, J0.58, which means this one here. RB here, J0.72, and then RC J0.36. So I plug all the value according to this standard formula here from conversion, from transformation to star to delta. And then I have the answer is XT equal to J2.46 per unit. And then from here, I need to find again the power angle equation during the fault analysis. So P1, again, saya terpaksa guna formula sama lah kan. Again, I have to find this one and then divide by XT, 2.46. 2.46 and then I have 0.5081. Okay, remember one thing, because this one is J, right? J, because XT is actually in magnitude. So this is actually 2.46 90 degree in polar form. When you convert from rectangular form to the polar form, so we care only the magnitude part, which means that 2.46. We doesn't care about the angle in degree. So 2.46, and then we solve it, we have 0.5081. Again, you have to check. You have to check the value for P naught. P naught is 1.329, right? We compare with this one, so we have 0.5081. So my answer is correct because it should be lower than 1.329. Dia kena kurang. Kalau awak dapat lebih, something wrong with your calculation during the fault analysis. Okay, then I have to find for the post-fault. Post-fault, very simple. We just open the circuit breaker. When you open the circuit breaker, the current cannot flow to this lower transmission line. It only goes to the upper line here. So when the fault line is open, after the fault is isolated. So straight away we can find the total reactance, which means that J0.22 plus J0.36 plus J0.72, which is equivalent to J1.3 per unit. And then again, I have to use this power angle equation here. And I have the answer is 0.9615 sine rectangle. And then how to check this one? I need to draw the power angle curve for all the condition. So I need to draw. So when I draw this one, sine waveform here, the power and the angle for each x-axis and y-axis. So I have, my answer is correct because the P-fault 1.329. When the fault occurs, 0.5081. When we isolate the fault, we have 0.9615. Jadi betul lah saya dapat tu. Sepatutnya in between. Post-fault tu mesti in between. Okay, then, okay, how to find this one? How to dalam bahasa Inggeris apa dia? Lorek. How to lorek dia. So, how to lorek? So, the best thing in order to know how to divide into two areas, area A1 and area A2. So, you draw like this. You draw like this, you define this one, P naught here, the power during P-fault. P2 here is the power after the fault, after we isolate the fault. And then the P1 here is the power during the fault. And again, we have to draw what we call as the area A1 equal to area A2. So then in here, we can see that this is actually the initial angle. Initial angle during the fault when the rotor is try to run. So initial angle, then we have the maximum angle here, and the clearing angle must be in between initial angle and the maximum angle. Dia mesti berada di antara maximum angle and initial angle. Tapi yang paling pentingnya how to draw. One thing you need to remember, after you write P0, P1 and P2, you need to draw the dotted line for the motor power, which is, we assume that the motor power is equal to 0.8. Okay. During this time, at the motor power is 0.8, okay, at this point here, it will intersect between motor power and clearing angle. Okay, for a clearing angle. If you want to draw for the area A2, apabila awak nak lorek dia, if you want to lorek dia tu, A2 ni, it means that it occurs at after the fault you isolate at P2 here. But for the for A1, area A1, okay, you need to remember one thing, area A1 is actually before the fault occurs, which means that you need to include this one, P0 here. So this is the reason why I sketched the one in black in color, gray in color here. So it means that it touched here. It touched during the initial angle at the pre-fault condition here. So this one, I draw like this. But for the post-fault, it means that at this point, I cannot draw at the pre-fault here because this is actually not the correct answer. The correct answer should be at area A2 must be after we isolate the fault, which means that saya kena lorek kat sini lah, kat A2 ni. So right now, after I already draw the area A1 and area A2, the next thing to do, I need to find the initial angle, which means that the sine inverse mechanical power divided by the initial power, P0 PM divided by PM. So 0.8 divided by 1.329. So I have 37.01 degrees. Means that at this point, the initial angle is 37.01 degree. And then I have to find the maximum angle. The maximum angle by using the standard formula here, 180 degree minus sine inverse PM, motor power divided by P2. You can see that from this equation here, you can see that the PM and the P2 here. Nampak tak PM P2 ni? Sebab tu saya lorek kat sini. Minus sine inverse PM bagi P2, nampak? PM bagi P2. Sebab tu saya lorek dia berada antara PM dan P2 untuk area A2. Kalau untuk area A1, PM divide by P0. Jadi PM by P0 sini ya. Okay, alright. From here, from maximum angle, we have 123.695 degree. Okay, right now, I want to find critical clearing angle, delta CR. How to find critical clearing angle? This means that I need to mention one thing. The area A1 must be equal to area A2. This is need to find the area A1 by using the integral area A2. But the most important thing, this one, cos delta CR. This is the basic formula to find the critical clearing angle, delta CR. Then from here, you just put all the value, the necessary value that you already calculate or given in the question. Motor power is 0.8. This one is maximum angle in radian minus initial angle plus power after the post fault. Cos this one is in degree. minus this one 0.5081, which means that the P1 max cos the initial angle 37.01 degree, divide by P2 max minus P1 max 0.9615 minus 0.5081. So I have the answer is 53.247 degree, which means that it's actually in between maximum angle and initial angle, 53.247. All right. Okay, from here, after you determine the critical clearing angle, delta CR, after that you have to find critical clearing time by using the standard formula here. So TCR equal to square root 2 times initial constant times the critical clearing angle minus initial angle. So you just plug in all the value that you determined earlier, and then you can have the answer is 0.502 second. Okay, then remember one thing, because in the given question asked you about, let's say if you want to shorten the clearing time by 75%, it means that from 100% to 75%. Which means that you have to find the critical clearing time the new critical clearing time, TCR new. Which means that 100% equal to 1 minus 0.75 times 0.501. And then we have the answer should be this is actually typing error, 0.03755 second. And again, by using this TCR new, you have to find the new setting of critical clearing angle. By manipulate this equation here, you can find the critical clearing angle, which is equal to 0.6637 radian or equal to 38.02 degree. Okay, this is how you calculate according to the question. If you want to shorten the clearing time by 75%. If you want to find if you want to shorten the clearing time by 75%, you must calculate the new clearing time, critical clearing time, and also you need to calculate again the new critical clearing angle, which means that the delta CR new. Okay, want to take a break about 2 minutes, then I will continue on last question, because this one is actually I need to add again a question here. Okay, I take a break about 2 minutes. I will continue on this one.
Doktor, kalau nak tanya boleh?
Boleh.
Doktor, yang tadi kan? Yang soalan tadi tu.
Okay.
Yang A1 equal to A2.
Oh, okay. Saya tengok balik. Okay, alright.
A1 equal to A2 kan banyak calculation dia sebelum dia sampai cos LCR kan. Yang calculation yang formula banyak tu nak kena tulis juga tak? Kau tak payah?
Yang mana? Yang ni ke?
Tu.
Tak payah.
Oh, yang
tak payah.
sikit je lah.
Tak payah skip. Awak tu terus tulis yang ni ke?
Oh, okey doktor.
Yang ni. Terus tulis yang ni saja. Ni. Tapi kena hati-hati bila masuk nilai ni sebab dia macam mana nak cakap, ada yang radian, ada yang degree, kena hati-hati sini lah.
Oh, faham.
Okay. Baik, sama-sama. Tak perlu ni, tak perlu tulis ni, just untuk saya punya apa nama, saya punya solution memang ada lah, tapi tak perlu tunjuk. Yang kamu kena tunjuk yang ni. This one you need to show. Because this one you need to obtain the critical clearing angle. Ini kena cari. Okay, I'll go to the last question. Okay. This one actually a very simple solution, but you need to understand first the concept of power system stability. Let's say we have a two-pole. We have a two-pole 50 Hz synchronous generator, which means the alternator rated at 200 megavolt ampere. This means that the rating of this synchronous generator. And then we have the power factor 0.7 lagging in connected in parallel with the last power system. So the generator have as a store kinetic energy of 1,200 megajoule. Okay, and then we have initially supply 85 megawatt to a load while operating here. Under the power angle of 5 degree vertical. A sudden disturbance occurs when the entire load is disconnected unexpectedly, resulting in an imbalance between the mechanical input power and electrical output power. This causes the generator rotor to accelerate, leading to concerns regarding excessive rotor angle deviation, transient instability, and potential mechanical stress on the machine. As a power system stability engineer, perform the following analysis. Determine the initial rotor acceleration immediately after the sudden load rejection. Part B, assuming the rotor acceleration remains constant for a period of 10 cycles, calculate the new power angle of the generator, the rotor speed in revolution per minute, RPM, after the disturbance. For part C, you propose a suitable stability enhancement strategy to improve the transient stability performance of the synchronous generator system and reduce the risk of instability following the standard disturbance. So actually this is how you solve this kind of question. You just write back the rating, the power factor, the frequency, number of pole, kinetic energy stored at synchronous speed, which means that WK. And then we have the initial real power output, PM equal to 85 megawatt, and then we have the initial power angle, which means that kalau initial ni maksudnya delta naught tau. Initial power angle delta naught equal to 5 degree. Okay, then load suddenly disconnected, which means that electrical power output becomes PE equal to 0. And then during of acceleration, 10 cycles. Okay, at 50 Hz, which means that 10 divided by 50 equal to 0.2 seconds. It means that this is actually belong to the 10 cycles. This is frequency. So we have 0.2 second. Okay, this kind of question is actually belong to the swing equation. So the swing equation, you need to understand first. This one here, this square delta over this square, this one is actually the acceleration power. PA, if you remember one thing, the basic equation, PA equal to mechanical power minus electrical power. Okay, this is the explanation. Actually, what is H, what is alpha, what is omega S. So first thing you need to do is you need to calculate first the initial constant. So this constant is H equal to WK, kinetic energy, divided by S base, which means that 6 megajoule per megavolt ampere. And after you calculate the initial constant, the next thing to do is need to find the synchronous speed. I know that this is basically the basic formula, right? I think already learn machine, right? Electrical machine. So by
by right you already know this formula. Synchronous speed equal to 120 times frequency divided by number of pole. So we know that from the given question, the frequency we already know, 50 Hz. Number of pole is equal to 2. So we have the synchronous speed is equal to 3000 revolution per minute. So we have 3000. So in order to find another one, which is the electrical angular velocity, you have to use omega s equal to 2 pi f, which means that 2 pi times frequency 50 Hz. So we have 314.16 radian per second. And after that, you have to find the accelerating power. Before this turbine occurs, the mechanical power is actually equal to electrical power equal to 85 megawatt. After the load rejection, which means that electrical power is equal to 0. Therefore, the PA equal to PM minus PE. Sekejap, saya tukar color. Okay, so the power equal to mechanical power minus electrical power. 85 minus 0 equal to 85 megawatt. And after that, you have to find, you have to determine the rotor acceleration by using this standard formula here. The alpha is equal to omega s time divided by 2h times the acceleration power. And then you need to convert the megawatt to per unit. Okay, megawatt to per unit. So we have 85 megawatt divided by 200 megawatt. So we have, which means that the actual divided by base lah. Because the base we know that equal to 200 megavolt ampere, this one, the base here, the rating here, 200 megavolt ampere. So from there, so this is the reason why 85 divided by 200, so I have 0.425 per unit. And then I have to calculate the initial acceleration according to this formula here. So I plug in all the value, the omega s, the synchronous speed, divided by 2 times the initial constant given in the question, and then times 0.425 here per unit. So I have the initial acceleration of the rotor is d square delta over t square equal to alpha is equal to 11.12 electrical radian per second square. And then after I found the initial acceleration rotor, I need to find the new power angle. The new power angle and rotor speed after the 10 cycle. I assume the acceleration is constant and the time is equal to 0.2 second. So I need to calculate the rotor angle deviation. Okay, deviation means that this one. This is actually the deviation. The data here is actually the rotor angle deviation. By using this standard formula here, rotor angle deviation equal to half times the acceleration time the t square. Because I know that from part A here, 11.12, and then t is equal to 0.2 second here. So I have the rotor angle deviation is 0.224 radian. And of course, I need to find also in degree, right? In degree. So by using the standard formula here, times 180 degree divided by pi. So I have 12.74 degree. And of course, I want to find the new rotor angle. It means that I need to find the new rotor angle equal to initial angle plus the rotor angle deviation. Rotor angle deviation plus the initial angle. So 5 degree plus 12.74 degrees. So I have 70.74 degree, the new rotor angle. And then I need to calculate the rotor speed increase. The speed deviation delta omega equal to alpha times t, which means that 11.12 times 0.2, so I have 2.224 radian per second. I know that for the earlier formula, the synchronous speed in radian per second, omega s equal to 314.16 radian per second. The new rotor speed, omega r equal to 314.16 plus 2.224 equal to 316.384 radian per second. And then I want to convert. I want to convert to RPM. This means that n equal to omega r divided by 2 pi times the 60. N equal to 316.384, which means this one, times 60 divided by 2 pi. So I have 3021.2 RPM. Okay, again, after you finish all this calculation, at part C, asking about propose a suitable stability enhancement strategy to improve the transient stability performance of the synchronous generator system and reduce the risk of instability following the sudden disturbance. So I already highlight this one. Okay. You can use the fast governor control, primary frequency control, or you can use fast excitation system and automatic voltage regulator, or you can use the power system stabilizer. Power system stabilizer, its function is to detect rotor speed oscillation to produce damping torque to reduce electromechanical oscillation. Or you can use the fast load restoration or control load shedding, or you can use the energy absorption using the braking resistor for severe disturbance. So this is okay. This is actually the recommended strategy to improve the strategy to improve the transient stability performance of the alternator system. So I stop here, but I want you to do this one again. I will share this question after this, so you can do it again. Okay, I think I stop here because it's already 10:48. Saya ingat saya stop sini lah.